What can I help you with?
So I was going back looking at the homework questions, and like I get this mathematically, but I'm kind of having a hard time remembering the order what to do, and that's with finding the percent abundance of an isotope.
Finding the percent abundance of an isotope.
Yeah.
Okay, so let me share my screen with you. So if you have only two isotopes of an element, it's pretty easy to figure out the percent abundance. It's just a little bit of math.
Mhm.
So you start off with the atomic weight is the sum of the mass of isotope 1 times the percent abundance of isotope 1 over 100. And here, I'm just going to do that. And I'm going to put X here, whatever the isotope is. So this means the mass of isotope 1 times the percent abundance of isotope 1 over 100 plus the mass of isotope 2 times the percent abundance of isotope 2 over 100. And you keep doing that for as many isotopes as you have. Okay?
Okay.
So this is what you do if you have many isotopes. But if you only have two, it's just this equation right here.
Well, that's what I thought, but I got really confused when I was looking at the homework solutions, and it's doing this whole thing with the x plus y equals 1.
Well, if we let X equal to percent abundance of 1 over 100 and Y equal percent abundance of 2 over 100. And remember, percent abundance of 1 plus percent abundance of 2 is equal to 100, right?
Mhm.
So if I divide each of these by 100 and this by 100, we get percent abundance of 1 over 100 plus the percent abundance of 2 over 100 is equal to 1. Do you follow me here?
Yeah.
So here, if you let X equal this whole thing and Y equal this whole thing, you're actually calculating that. And when you finally do find out what X is, you can solve for the percent abundance because it's going to be X times 100.
Okay, that makes sense.
Okay. And also, if you let this be X and this be Y, then you can also say X plus Y equals 1. And Y is equal to 1 minus X.
Okay.
So this whole thing becomes AW is equal to mass of 1 times X plus mass of 2 times Y, which is mass of 1 times X plus mass of 2 times 1 minus X. And here, this is mass of 1 times X plus mass of 2 minus mass of 2 times X. And then you get atomic weight minus mass of 2 is mass of 1 times X minus mass of 2 times X. And then you get atomic weight minus the mass of 2 is X, mass of 1 minus mass of 2. And then finally you get that the atomic weight minus the mass of 2 over mass of 1 minus mass of 2 is equal to X. So you just plug numbers in then.
Okay, so would you use the y equals 1 minus x kind of thing if you don't know what the fractional abundance is? Is that
right? That's exactly
okay?
it. If you don't know the fractional abundances, you use this to figure it out.
Okay. I'm just getting lost in like a sea of x's and y's.
Well, you got to be able to follow the algebra.
Yeah.
And here, I tried to lay it out for you very step by step.
Yeah, no, I see.
And you got to be good at that.
Mm-hmm.
You got to, you know how your algebra teachers say, don't skip steps because you'll make mistakes?
Yep.
They're right.
Yeah.
You're absolutely right. Okay. So I don't know if that helps you out at all.
No, it does. Just tripping
All right.
myself up.
Now, what else can I help you with?
I would like to go a little over naming formulas when you have when you just have like, I don't know what's the word I'm looking for. Like if if it says like silicone chloride 4 and it's silicone tetrachloride, it's like I know you have to get the charges of it, but I keep getting like the ion one and like the regular covalent one mixed up.
Okay, first of all, when you want to know how to name something, you got to look at the formula.
Mm-hmm.
If the formula is a metal and a non-metal, it's ionic.
Yeah.
If it's not a metal and a non-metal, it's probably molecular. Silicon is a metalloid, not metal. So this is probably a molecular formula.
Okay.
And there are two different ways of naming these things. Molecular formulas, you name this one silicon tetrachloride, excuse me. So that's how you name this guy. Now, if silicon were an ion, this would be silicon 4-chloride. Because that's how you would name silicon if it were an ion, silicon 4, because it's got a +4 charge. But it's not ionic, it's molecular.
Okay. All right. Okay. Because they're both negative. They're both
Not because
anions.
they're both negative, because this is a metalloid.
Oh, okay. I see.
And this is a metal. And this is a metal. So when you have a metal and a non-metal, it's ionic.
Okay.
And if you have a metalloid and a non-metal, it's molecular. If you have a non-metal and a non-metal, it's molecular.
Okay.
So you use that periodic table to help you decide if you have a metal or not.
Okay.
So do you know how to name these two?
Oh, they're ionic, so it's sodium. Everything my brain has left me.
Well, you should be able to look at the periodic table and know the charge on each of these. Sodium is in 1A, so it's +1.
Yeah.
Chlorine is in 7A, so it's -1.
-1. Yeah.
And here, this is called sodium ion. This is called chloride ion. To name the whole compound, you put these two together.
Sodium chloride.
Right. And you leave off the words ion. And you might say, well, why am I leaving off ion? How do I know this is ionic? And the answer is that's a metal. And that's a non-metal. That's how you know it's ionic.
Mm-hmm.
For this one, there's one nickel and there's 2 chlorides. Now the chlorides are always -1 in ionic compounds, always.
Mm-hmm.
So what's the charge on nickel? It has to be +2 because the total charge has to be 0. So that's why this has to be a 2.
Mm-hmm.
So the name for this one is nickel 2 ion and chloride ion. And so you get nickel 2 chloride. And you'll notice I don't use any sort of prefix here for the chlorines. It's just chloride. And you might wonder, well, if I have that name, how am I supposed to know there's 2 chlorides? And the answer is, you know, this is nickel +2 because it says so.
Mm-hmm.
You know, this is chlorine -1 because it's in group 7A. And you have
Okay.
to figure out how many of each do you need to get a neutral charge? And what's the minimum amount you need, not the maximum?
Mm-hmm.
And can you see if we had another chlorine here, that would be a -2 and a +2, and that's
Yeah,
neutral.
of course. Yeah.
So how do you write that? So here, this name here, we don't have to tell people there's 2 chlorides. We can figure it out.
Okay.
But we do have to tell people that nickel is a +2 charge because you can't figure that out necessarily.
Mm-hmm.
Turns out that from this formula, we can figure out that nickel's a +2 because the chlorines are -1s. So what does that have to be?
I'm sorry, which one?
Right here.
So if there was just one nickel,
Uh-huh.
then does that mean it would be a molecular?
No.
No.
Nickel is a metal.
Okay.
If these are both -1 because they're in group 7A, then what does that have to be so the whole thing's neutral?
It would have to be +2.
That's right. And that's how I know it's nickel too.
Okay.
So whenever you're given the formula of an ionic compound, you should know the charge on at least one of those ions, either because you're given its name or because you have memorized the charge.
Okay. And then like for the molecular one, which is what I was kind of wondering. So you got silicone and then chloride, which is marked 4, but the tetrachloride, and you do the, I know you have to do some math with it, and it's like silicone has a, is that, am I right?
There's no math because there's no ions.
Okay.
So this is carbon dioxide. This is dinitrogen monoxide.
Okay. For some reason, I was thinking tetra was 3. So
Oh no, tetra's 4, tri is 3.
okay.
Think tricycle.
Yeah. I don't know why I thought that. It was really confusing me.
And this one would be called dihydrogen monoxide. So notice for the first element, you only use a prefix if there's more than one.
Mm-hmm.
And for the second one, you always use a prefix, always.
Yeah.
So that's how you name molecular compounds. And we have not learned how to name molecular compounds with 3 different elements. Like you don't know how to name this guy unless you happen to recognize it.
That looks familiar. I don't know.
It's one of those two.
Mm.
This is the formula for fructose, and this is the formula for glucose.
Okay.
So you recognized it, but you didn't remember the name.
Yeah.
But we don't learn this type of naming in this class.
Okay.
Sometimes we memorize some of these.
Mm-hmm.
So that's molecular.
Okay. Yeah, I was just getting them confused. So just to reiterate, I didn't write very good notes apparently. So it's a non-metal and non-metal, then a metal and non-metal is molecular.
Yeah, molecular is non and non.
Okay.
Most of the time.
Okay.
Here's an example where non and non is not molecular. This is ionic. And the reason you know this is ionic is because you have memorized this is an ion.
Mm-hmm. Oh, okay.
So whenever you see that, you're supposed to think ionic.
Okay.
And of course, what's the other ion here?
Chloride.
Right. And this would be called ammonium chloride. Okay?
Mm-hmm.
What else can I help you with?
I did have a question from the lab earlier this week. It was the mass spectrometry one.
Okay.
Most of it I went through pretty easily, but there was one, let's see if I can find it. And
Is
he
it in
said,
the homework or the lab?
sorry, what?
Is it in the homework or the lab?
It was the lab.
Okay.
So it was actually, it was like towards the end, and he said combine relative probabilities for the M/0 ratio.
Right.
And you had the different intensities. And I was a little confused about like how this worked out. So BR79 was at 100, and then BR81 was at 97.5 intensity.
Right. So the way you do this, I'm going to make just a big old table here. And so I'm going to call this BR79, which is 100 for intensity.
And
this one's
yeah.
89, which was 797.5 for intensity, right?
Yes.
So they're pretty close, agreed?
Yeah.
And I'm going to call this one 79 with 100. And this one 81 with 97.5. Okay, so this box you can see is a 79 and a 79. So I'm going to put 79, 79. This box is an 81, 79. So you can see I'm doing the top one first, right?
Yeah, sure.
So again, the top one first. And here, you can't tell I'm doing the top one first because they're the same. So how much does one of these weigh that has two of these?
That'd be 158.
And how about this one?
That one's 160. Is that what we pointed over? Oh, no. Oh, yeah, 160.
And how about this one?
Also 160.
And how about this one?
And 162.
So when we talk about relative intensities, all you do is multiply these two numbers and leave it like that, or I like to multiply these two numbers and divide by 100.
Okay.
So what's 100 times 100 divided by 100?
100.
And that's why I like to divide by 100.
Okay.
What's 97.5 times 100 divided by 100?
97.5.
Now, these are relative intensities, meaning if you had these two combined, it'd be a peak of 100. If you had these two combined, it'd be a peak of 97.5, almost as tall as that one. What's 100 times 97.5 divided by 100?
97.5.
See, we can do most of this without a calculator. Now,
Yeah.
This one is tough. What's 97.5 times 97.5 divided by 100? It's calculator time.
Yeah.
And I don't remember what it is. I want to say it's like 95.1.
It was 90. Yeah, it was 95.1.
Okay, 95.1. Okay, so now we make a list of these. 158, 160, and 162. The 158 is 100, right?
Yeah.
The 160 is 97.5 plus 97.5. And this one is 95.1. So if you add these together, you get 195. So the spectrum would look like this. And I'm going to write this as 195. So this would go all the way up to 195. Where would this go compared to this 195 if it's 100?
About halfway.
Yep, just a little bit more, right? Where would this go compared to 195?
Just like quarter.
A little less than halfway, right? Okay, now what if I wanted to make this, which is now a 195, this is a 95.1, and this is a 100. How can I make this look like more of a normal spectrum where this is 100?
Oh, you would have to calculate the percentages.
Yeah, just do this. Divide by 195 and multiply by 100 and you get 100.
Oh, okay. I see why you did that.
Now, if I
Okay.
divide this one by 195 and multiply by 100, I have to do it for all of them.
Mm-hmm.
So if we look at this one, we get 10,000 divided by 195. And so this ends up being 51.28. And this ends up being well, not that. That's clearly wrong. I get 48.77. So here I've made it look like a normal mass spectrum that you get from using the instrument. How would I turn these numbers into percentages if that were asked? So this is, remember, this one here is 100. This one is 195, and this one is 95.1. How would I turn these into percentages?
Good question.
Percentage is part over whole
Right.
times 100%. So if we want to do the percentage for the 195, that would be 195 over 100 plus 195 plus 95.1 times 100.
Okay.
So the whole means all of them, and the part means the one you're interested in.
Mm-hmm.
So this one would be 195 divided by 100 plus 195 plus 95.1, and then times 100. So this one would be 49.98%, if I did that right. And let me think about that for a minute. Yep. So this peak would be 49.98%. And you can see that this one would be about 25%, and this one would be about 24%, something like that.
Yeah.
And these all add up to 100.
Okay.
So there's a lot of ways you can manipulate the data so that it looks the way you want it to look.
Mm-hmm.
If you want percentages, you do part divided by whole. If you want intensity, you divide by the biggest peak and then multiply by 100, so you get 100.
Okay.
So these are little tricks of the trade where we're doing things that are okay algebraically, and that's what you do. Okay.
All right. So, okay, that makes a lot of sense. Yeah, I just didn't calculate the intensities after I did the Punnett square, which is why I got confused.
Yeah. And you just multiply these two numbers for a pair.
Mm-hmm. Yeah.
Now you could also do this without dividing by 100. In which case here you wouldn't have 100, you'd have 10,000. And here you'd have 9,750, 9,750, and 9,510.
Mm-hmm.
So over here, instead of having 100, you'd have 10,000. And instead of having 97.5 plus 97.5, you'd have 19,500. And here you'd have 9,510. So if you put these on a graph, what would they look like? Here's my tiny little graph. Well, if this is 19,500, that would be about 10,000, right?
Yeah.
And this would be about 9,510.
Yeah.
Doesn't that look like that?
Uh-huh.
How do we turn this into 100%? Well, divide by 19,500 and multiply by 100, and you get 100.
Mm-hmm.
What do you do with that one? Divide by 19,500, multiply by 100. So it's all the same thing, only different. It's just, you know, what you're used to doing. I don't like working with these huge numbers. I'd rather do this.
Yeah, me either.
100 times 100 divided by 100.
Okay. That makes sense.
A lot of mathematics in the sciences, they try to make it so that the number comes out to be something easy to look at, like between 1 and 1,000. No one's really fond of decimals, so if we can avoid it, we do, but you can't always avoid it. One of the ways we do avoid it is we use prefixes. So if you have a prefix like 0.0424 grams, you can turn that into 4.24 centigrams, and it's the same thing. And now I don't have a number that's less than 1. So this is science tries to get around decimals or numbers smaller than 1.
Okay.
It's also how we get rid of like huge numbers, like say, we don't want to write out 1,607,000, so we have 1.607. In this case, mega. So we'll call this meters. So megameters.
So like how far down do you expect us to know those? Like past the milli? I had them all written down.
So you should know big M, little k, little d, little c, little m, micro, nano, and pico.
Okay, that's not that bad.
Here, it's 10 to the 6, 10 to the 3, 10 to the -1, 10 to the -2, 10 to the -3, 10 to the -6, 10 to the -9, 10 to the -12. You'll notice most of them skip by 3s.
Yeah.
And these are kind of the odd ones.
Okay. Oh, sorry.
All right, Melissa, we're just asking questions. If you have any, feel free to ask.
Is there anything on our little note card that we can have on the exam? Is anything banned, or can I just have all my formulas on it?
You can have all your formulas on it.
Okay.
The only thing that's banned would be like bad language. Something inappropriate like I hate chocolate. That would be inappropriate.
That would be.
Very inappropriate. I'm teasing. You can hate chocolate. It's okay. I just don't like you if that's true. Actually, it doesn't mean I don't like you. It just means I don't understand you.
Well, I wouldn't understand somebody who doesn't like chocolate either. That's just a hate crime.
Yeah, it's not the top of the food pyramid. It's the base. Okay. Any other questions?
How should I have all of my polyatomic ions on my little note card, like the formulas and the charges?
Yeah, unless you can memorize them.
Okay.
You should try to memorize them.
Well, I'm trying. I am. I don't want to screw up. So
right.
Yeah.
This morning we were talking about the note card, and one of the things you can do for your next exam is you can start writing down all the things you think you need to know from chapter 3 and from chapter 4 and from chapter 5 as you're going through the chapters.
Okay.
And when you write all those things down on a big, huge piece of paper that's 8.5 by 11, you can then start saying, well, you know what? That's something that I don't want to have to remember, so I'll write it down on my note card.
Gotcha.
And the things that you start to recognize and go, oh yeah, I got that, you don't write on your note card. So your 3 8.5 by 11 sheets of paper get whittled down to a note card very quickly. And I was also explaining to someone this morning, for me, on my note cards, I would put things that were odd, not quite normal, because I would memorize trends. And so then I would put other things on my note card that would, that I wouldn't necessarily see as a trend. Like, I might do something like this on my note card. To help me remember the charge on those ions.
Okay.
So you see it's a little staircase, 1, 2, 3.
I do.
So I might do something like that. What else would I do? I might put something like this down. Just to help me go from here to here for getting the formula that shows the relationship between a micrometer and a meter.
Okay, yeah, I've got those.
So I put things that are odd.
Okay.
Like I probably would not put the polyatomic ions down, but I would probably do this. So this means that if you have the 8, you can get the ite.
Yep.
And so if someone says sulfate, SO4 2 minus, and on the test it says sulfite, you go, oh, SO3 2 minus. Because that's the relationship between 8 and ite. One less oxygen for the ite. So again, that's what I end up usually putting on my note card is little, what I almost think of as trivia.
Okay.
Rather than patterns, because I'm really good at recognizing patterns. And I think most humans are better at recognizing patterns than we are at recognizing trivia.
Gotcha.
And if you're really good at trivia, you need to get on like Jeopardy or something like that. Okay. So I would say that the other thing I was going to mention is you only get in a 3.5 by 3 inch by 5 inch note card for the second exam. And that means that if you can't remember that stuff on your first note card, you're not going to have room for anything else on your second note card.
Yep, that's fair.
You're going to have 3 additional chapters of information. So you want to try and learn that note card pretty well. Also, another thing I didn't mention earlier to other people, but I'm going to mention it to you guys because it just popped into my mind. Once you have your note card fine-tuned, write it down again twice. And the reason you want to write it is because when you write things, you remember them better than if you just look at them. It takes more time, but you remember it better. That's the way it is for 99% of people. You guys ever get into trouble in grade school?
Not really.
Right on the board. I will not talk back to Mrs. Han. I will not talk back to Mrs. Han. You remember that. But on the other hand, do you remember that little poem you recited in second grade in front of everybody and you were really nervous? Do you remember that? Of course not, because you only said it. You never wrote it down. But it happened. You recited a poem. You may not remember it, but you did. But I guarantee you, when you wrote that down on the board 100 times, you remember it. So writing is essential to remembering things. And that's also important for these exams that you're preparing for. If you can't look at a problem and solve it without using your book, you're not ready for that problem. And so the only way to learn how to be prepared is to try those problems without looking at your book. And if you can't do it, figure out how to do it with looking at your book and find out, consciously, why did I get stuck? And the answer may be, I got stuck because I did not know where to start. So you're going to focus on learning, where do I start when I see a problem like this? And maybe you overcome that hurdle and then you reach another hurdle and you say, well, how do I get through this? And then once you figure it out, you got to say, okay, so when I get to this part, here's what I have to do. And when you start thinking about the steps to solving a problem, it's more meaningful than if Tony just writes steps out for you.
Mm-hmm.
Okay. What else can I help you with?
I had a kind of general question. So are we allowed to write on both sides of the note card or just one?
Are you allowed to what?
Write on both sides of the note card or just one?
Yeah, you can write on both sides, but not the edges.
Okay. I think I can do that.
All right.
And I'm still locked out at the quiz. It's still telling me I need an access code.
For the quiz or the exam?
The module 2 quiz.
The module 2 quiz. Well, can you hang out a little bit later and we'll check into that?
Sure.
Okay. Anything else, Ellen?
I don't think so. I'm gonna do a few more practices of that isotopic abundance before I start, but that was what was really.
Okay, well, then I'm going
Yeah.
to go ahead and end this meeting or stop recording.
Okay.
And I'm going to have we're going to take a look at what Melissa's doing there. Okay,
All right. Thank you.
you bet. Bye-bye.
Bye.